Hello, it's Mr. Burkhart, who has just finished going through all of the rest of this worksheet and realized that he never turned the stupid recorder on. So he is very sad and tired and confused and punchy. So, anyways, let's see where E starts. Oh my God, there was so much here. It was probably the best lesson I ever gave in my life and was not recorded for posterity. All right. So, retry. Here we have a cart. In case A, the cart is going to be pushed up the ramp with a force parallel to the ramp. And in case B, we're going to use a force which is horizontal to the ground. So they're just telling us that it's when the cart gets to a position, a length L up the inclines, right? So this is L here. You know what? I'm going to have to take a, here it is. I already took a, see, I'm proving it. I already did this. That was the last one I took. Here we go. So they're saying that this is a length L here, right? For both cases, it's going to go a length L up the ramp. So they're going to use L instead of X. There's force of gravity pulling down. There's a normal force. This one's got the same force of gravity and the same normal force. Well, is it the same normal force? We'll find out. But there is a normal force. And this is mg, and this is mg, omg. So here there's a so see, this force of gravity's got a component which is pulling it down the ramp, and then it's got a component which is balancing the normal force, or actually, equal to the normal force. And there's also a component here pulling it down. This one's got a component, and it's got a component that's pushing against the normal force. So the reason that this one is bigger is because the force, all of the force is, so this force is greater than the component that's greater than the weight. So it's definitely greater than a component of the weight. If it's greater than the weight, it's definitely greater than just a component of the weight. So we have a net force. So we have an acceleration. So we have a speed when we get up there. This one, it's only a component of this force is right. So we don't have all of the force pushing the cart. Some of the force here is going into pushing down on the cart, pushing it against the ramp. And some of the component of this force is pushing the cart up the ramp, right? So we have less force pushing the cart up the ramp than we had over here. So that's why it's going to be going slower. And here is what I just said, using a lot of words, and you can pause the video and read that. Using energy transformations, why is it different? Well, again, basically, we look at work. This cart here, we have work is equal to force times the distance up the ramp, which is L. All of the force, right? And so that's equal to the change in kinetic energy. So we have this amount of work caused by this amount of force changing this kinetic energy, giving it a velocity, VA. Here, the work is equal to just a component of the force, right? So we have less work done because the component of the force is always less than the total force. And so we have less work done, so we have less kinetic energy, so we have less velocity. And I'm sure that's what they say here. You should just go ahead and pause the video and read that. All right, using equations, let's do it with equations now. So the key principle is net work equals the change in kinetic energy. So the net work is equal to the net force times distance. The kinetic energy is equal to 1/2 the change in the velocity, squares of the velocity. So the component of the force, so the net force is equal to the force, the pushing force up the ramp, but you have to subtract the component of the weight from that. See, weight is trying to pull the cart down the ramp and the force is pushing it up the ramp. So the net force is the difference between those two forces. And that's what's going on right here. Right here. And instead of D, we use L, and the initial velocity is 0, so that goes away. So they skipped about 20 steps of algebra. They multiplied both sides by 2 to get rid of the half. They divided both sides by m to get rid of the m on this side. You can't just cancel them out because that doesn't work. Because if you multiplied this out, this would be FL minus mg sine theta L. Right? Everything doesn't have an m in it. So don't cross out the m's. Divide both sides by m to get rid of the mass on the right. The vi squared is gone already because it was 0. So then we took the square root. And that's a formula for the velocity of the thing up the ramp. And you can check the units. And then for B, we basically go through the same process. The net work is equal to the change in kinetic energy. So the force times the distance is equal to 1/2 m times the difference of the squares of the velocities. And then you write it all out. And you can see really the only difference is now instead of F minus mg sine theta, remember mg sine theta is the component of the weight pulling it down the ramp. We have to subtract that out from the force pushing it up the ramp to get the net force. So F cosine of theta is what's different about it, and we go through the same process, and you can see that that's why A is bigger than B, because F cosine of theta is always going to be smaller than F, or equal to F. I mean, cosine of 0 is as big as it can get. Cosine of 0 is 1, and the trig, as you run through trig functions from 0 to 90, they go from 0 to 1, right? So cosine of theta is going to have to be less than 1 if it's anything other than 0 degrees. And at any time, pause the video and read the words if you'd like to. Oh, good, run F. This is one of those deals where Dominique and Carlos are arguing about blocks. So I'm just going to talk here. And then I'll just scroll slowly through them so you can read the words. I'm just going to talk about what's really happening here. So they're going to argue about which ones are faster at the end and which ones have the most energy and which ones land first. So let's just talk about A, and let's talk about getting to the ground first. So B is going to take longer to get to the ground. And the reason B is going to take longer to get to the ground is because the time it takes to get to the ground is based on your acceleration due to gravity, or your acceleration, period. And B has got less acceleration than A and C. A and C both have 9.8 meters per second squared acceleration. B does not, because B is on a ramp. And so if you drew the acceleration vector, G pointing straight down, only a component of that is pulling the block down the ramp, which would have to be smaller than G. So B has less acceleration, so it takes longer to get to the bottom of the ramp. Let's talk about, so A and C will hit the ground at the same time because they're both in free fall starting at the same height. Let's look at energy. Who's got the most energy at the end? Well, C has the most energy at the end because C has the most energy at the beginning. At the beginning, A has got mgh, and at the end, it will have kinetic energy. At the beginning, C has got the same mgh, but it also has kinetic energy because it has a velocity. A is at rest, and C is not at rest. So C has the most energy at the end because it has the most energy at the beginning. It's got both kinds of energy at the beginning. B will be going slower when it hits the bottom of the ramp, so it will have the least energy of all of them. It has, well, you know what? I think actually A and B should have the same amount of energy at the bottom, even though it takes B longer to get there, because they have the same amount of energy at the top. How about that? Let me change my mind. All right, so you can go through and read, pause the video and read what Dominique is correct about, and read what Carlos was correct about, and see if they matched your answers. All right, you should be checking your answers. We're assuming that you're doing these assignments, and now you're checking your answers. Here's how Dominique is incorrect. Here's how Carlos is incorrect. And God help us, we're only in part B. All right, so now we're going to drop that block down a curvy ramp. And here's the free body diagram showing, notice that it shows that the normal force is a much longer line than the force of gravity. So that's very interesting. We should reflect on that and ask ourselves, why would the normal force line be bigger than the force of gravity when normally it should be smaller because it's a component of the force, right? There's the force of gravity, and the force of gravity would have a component, and the cosine component would balance the normal force, but in this case, the normal force is greater. Think about the centripetal experience this block is having as it goes down a ramp. All right, so Blake comes up with an equation for the work done by the normal force. And basically, long story short, the normal force doesn't do work because the normal force is always perpendicular to the displacement vector. The normal force vector is always at 90 degrees to the displacement vector at any time. And you have to have at least a component of your force vector in the same plane as your displacement vector for either positive or negative work to be done. So the angle is always 90, and the cosine of 90 is 0, so there's never any work done. All right, please pause the video and read the words. We're going to go ahead and finish up here with part G. The car, it's this thing here, and it's dropped down this loop-de-loop, and it goes around the loop-de-loop. Whee! And I had one of these when I was a kid. I loved it. It was a Christmas present. And it was Hot Wheels. So anyways, here's what the energy, so you can see there's a free body diagram. That should make sense to us. We've had that before, right? We had free body diagrams before. And notice the normal force is always perpendicular to the surface, so it's this weird thing where the normal force is pushing down and the force of gravity is pushing down. All right, what is going on with energy? Well, at the beginning, at the top, at position H, it's all potential energy. And when it's at the top of the loop-de-loop, there is potential energy and kinetic energy. Oh, thank you, Gilly. And could you make me some oatmeal? Yeah. Thanks. So there's potential energy and kinetic energy. Notice that the potential energy due to gravity is more than the kinetic energy because the diameter of the loop-de-loop is more than half of the height. And so, citing the bar chart, explain why the release height must be greater than the diameter of the loop. You need to have some kinetic energy to get over that loop, right? And if the diameter was the same as the height, then all of the energy when you got to the top of the loop would be potential energy again, and there wouldn't be any kinetic energy, and there wouldn't be any motion, and it would stop, and then it would drop, and then it would roll. And there, we can pause the video and look at that. That's what I just said. That's what I said. Carlos comes up with an equation. I don't know where he got this crazy equation. And then he tests it, and Carlos has got a cool thing that can sense normal force. I have no idea what that might be, but I need to get into the science catalog and buy me a normal force measurer that can measure normal force. That would be cool. Anyways, Carlo runs the experiment and gets a graph, and the graph does not support the equation at all because the equation is an inverse equation. It's just like saying y equals 1 over x, right? 2mg is constant. That's like the number 1. 1 is constant. 2mg is constant. So that's like y equals 1 over x. So y equals 1 over x equation. Actually, I'll just go ahead and maybe I should do these twice. I feel like this lesson is actually better than the first one. 1 over x looks like this, right? That's what the graph would look like. And that is a linear graph. It's showing us that there's a direct linear relationship between the normal force and the height that it's dropped. So the higher you drop it from, the more the normal force is, linearly. So no, the data are not consistent. No. And Blake suggests the normal force does not depend on R. The normal force will depend on the speed of the cart, which depends on R. And there you go. If we release it from point 8, the car does not complete the loop. Look at the graph. The graph says you have to have at least 1 meter of height to, if you have 1 meter of height, your normal force will be 0, which would be like the breaking point, right? Anything less than that, and there's not going to be a normal force, which means you're in free fall. You're not touching anymore. And so we'll just leave that there so you have enough time to pause it if you want to look at it. All right, we did H already. Yay. So let's stop